Hello and welcome to this talk, Four Steps to Data Architecture for Analytics. I put this together because I've experienced a lot of instances in my consulting time where people struggle to figure out how to move to architecture. What is architecture? How do I define architecture? How do I implement architecture? And how do I make this whole architectural thing happen? So we use the term data architecture a lot. But often I've observed in consulting that we're really not very good at making data architecture happen. So I'm Dave Wells. I'm the education director and also an instructor at eLearning Curve, as well as an active consultant in the industry. And so what I bring to you in this session is based on experience from consulting, as well as interaction with a lot of my tech education colleagues. I want to begin with the idea of why we need to rethink data architecture. Certainly, we've had data architecture for a long, long time. And most recently, I think most of our data management architectures are based on the data warehousing concepts of the 1990s. So what we've had recently in the last decade or decade and a half is what I refer to as the data quake. And it's a lot of changes in the world of data that shake up the foundations of what we know in data management in the same way that an earthquake shakes the foundations of what's built on the surface of the earth. So at the left side of this slide, you see a lot of things that are familiar: relational database management systems and data warehousing and entity relationship modeling and ETL, and it sort of continues from left to right. Up to business intelligence is the place where most of our data management architectures today are founded. But then we've experienced all of this other stuff that shakes it up: big data and Hadoop and complex data pipelines and schema on read access to data, and microservices and containers and edge, data science, AI, machine learning, NoSQL. All of this stuff shakes it up. And what I see so much of out there is taking our 1990s data warehousing architecture and trying to bolt on capabilities to handle NoSQL and big data and data lakes and so on and so forth. And it's sort of a duct tape and Band-Aid approach. And it gets us by in the short term, but it's not sustainable. So we have to think of this data quake as a message that maybe it's time to stop and rethink data management architecture, because there are so many different requirements in this world of analytics that we need to approach it in a somewhat different way. And we can't continue to Band-Aid and duct tape on new features on an architecture that's predicated on batch processing of data in an ETL form. So today's data management complexities are quite different. Modern data management, we have a lot of things going on. If you look at the data sources, we've got all the traditional sources: the software as a service applications, ERP, our legacy systems, all of our transactional systems. But now master data management has become not just a place where we integrate data, but also a source for all sorts of analytics activities. And then we've got all the big data stuff: web and social and commercial data, sensors and open data. So we have just changes in data sources. And then how we control the management of data. Data cataloging is the next generation of metadata management. And how we manage data in catalogs is important. And the catalog thing can be quite challenging, because if we look back as recently as 7, 8, 9 years ago, organizations tended to have one data catalog if they had one at all. Now, every product you buy, every self-service analytics product, every data pipeline product, every product that you bring in for data management tends to have an embedded data catalog. And we don't want to propagate metadata in lots of different places and have proprietary metadata based on these catalogs. So one of the things we have to think about is, what's the enterprise data catalog? What's sort of the master copy of metadata? And then we've got all these other issues around semantic modeling and aligning big data with business semantics. Data governance has become more complex. We have all sorts of data governance challenges as regulations and data privacy concerns and security concerns with the prevalence of data breaches, and all of that stuff increases. The data provenance and the data lineage we need to care about and pay attention to, because that's about the trustworthiness of data, and that's also about the troubleshooting when things go wrong. And then there's this idea of data connectors. How do we connect with the data? And lots of these big data sources, we need custom connectors to access them. They're not SQL ODBC compliant, so we need the ability to connect with them that way. But there's also this idea that we can build our own data connectors, and this should be of special interest to data architects. The idea that I can build data connectors so that a consumer of data, a data scientist, for example, can say, I want you to access this JSON data in the data lake, but return it to me as rows and columns in a table form because I want to process it that way. Or maybe vice versa, I want you to access this relational data in the data warehouse, but navigate those relationships and return it to me as a graph. So if we create those kinds of data connectors, that's an architectural concept about how we connect with data, and it's an opportunity to build reusable components so we support this whole schema on read concept in a very graceful way and without a lot of handcrafting. Then we've got all the stuff around data pipelines, data flow, ingestion, integration, transformation. It's no longer simple ETL. It's a lot of different ways of doing things with data synchronization, with data stream ingestion, with change data capture, and so many things that go into this mix now. And then the data sharing, it's no longer the data warehouse, that goal of single version of the truth. And that single version of the truth was rarely realized. I've done some recent polling and found that 60% of organizations say they have between 2 and 5 data warehouses. Very few organizations have only one data warehouse, and nearly 20% have more than 5 data warehouses. So we've got this multiple data warehouse scenario as well as having built data lakes. And now we have to think about how data lake and data warehouse work together, as well as how they fit with master data management, reference data management. And again, the data catalog comes into play as we provide metadata about all of this shareable data. And also we now have data scientists and data analysts creating user data sets that are shareable with others, and we may want to catalog those. The whole data access thing is challenging. It's no longer simple query. We want file access. We want APIs, and API management has become its own large complex thing. We've got the issues around data services. Then we've got this idea of analytic sandboxes where we can load the data as a data analyst or data scientist, explore it, play with it, experiment with it. And if we mush it up, flush it and reload it and experiment some more. Our applications, once as simple as BI and reporting, now include analytics, advanced analytics, data science, artificial intelligence, machine learning, and that replicates through to our data consumers. Still, we have the report writers and the business and data analysts, but we also have the data scientists, and not all of our data consumers are people anymore. We're sending data directly to applications and algorithms and doing automation kinds of things where there's no human intervention in our data consumers, our computer processes. Add the complexity of our deployment platforms. It's not just on-premises, it's not just cloud. It's on-prem, cloud, multi-cloud, and these hybrids of cloud, multi-cloud that make it complex when we have data and processes that span across all of these things, multiple cloud environments, plus on-premises servers. So it is a much more complex world we're working in as far as data management than if we roll back the calendar as little as 15 years to our age of data warehousing. So it's quite different. At the top, you can see here what a BI data architecture looked like in a 30,000-foot view in a sort of an abstract form. We had sources of legacy systems, OLTP systems, and some external data. We managed it in data warehouses, master data repositories, and ODS. And we produced dashboards and scorecards and OLAP and reporting to support a limited number of consumers. On the bottom is analytics data architecture at the same abstract level. All the things in red are things that we've added, different kinds of data, geospatial, machine, IoT, social, commercial, and so on. So we've added new kinds of data, and it's not data that necessarily comes to us as structured data. We're managing it in different places, data lakes, analytics sandboxes. We're using it in many more ways, exploration and discovery and forecasting, prediction, prescription, and even hands-off automation, robotics, software bots, hardware bots. And then the consumption, no longer just BI and report consumers, all the data analysts, business analysts, data scientists. And as I mentioned before, the apps and algorithms where the data access and the data consumption is from computer to computer with no human intervention. So it's a different world. It's complex, it's challenging. Putting together the architecture for this stuff is hard. We need to move from linear data flow to multi-directional, from rigid workflow to agile workflow, from structured data to structured and unstructured, from enterprise data to enterprise and external, from batch to batch stream and real-time processing, from accepting data latency as the norm to responding to the demand for fast data, data at the speed of analysis, from rigid scale-up kind of infrastructure to elastic scale-out, and from central services and IT dependency to self-service autonomy. And self-service is one of the big pushes for rethinking data architecture. The number of data consumers out there has exploded massively as we move data access from being something done by technical people to data access and data analysis as something that's done by people in business offices. So a modern analytics architecture then may look something like this. I've got all of the data acquisition stuff, sources, the data capture, the data ingestion. And let me point out a couple of things in there. Under capture, you see change data capture, CDC, the ability to recognize changes in a database when they happen. When we couple change data capture with stream processing, we can take your legacy systems, your OLTP systems, many of your systems that are currently running batch ETL processes, and we can move them to real-time or near real-time with a combination of CDC and data streaming. So we're less disruptive to the source system and moving data faster, meeting today's demands for fast data. So these are some of the kinds of architectural concepts we want to build in as we do this. When we move from data acquisition to what used to be data integration, now we want to think of it not as integration, but as data refinement. There are so many things we do in changing data, and it's not always integration. And sometimes when we integrate data too much in a data warehousing style, we take away analytic opportunities. When we cleanse data too much, we take away analytic opportunities. So we want to think of data refinement in a different way. We want to land data in its raw form so that data scientists who need raw data can get to it before it's been transformed. Then we want to refine it with the standardization and the kinds of formatting things we want to do, standardizing dates and maybe some light cleansing and those kinds of things. Then we may want to integrate it, make it look more like a traditional data warehouse. And then we may want to aggregate it, make it look more like dimensional data marts. And we also want to support that discovery zone, which is the data sandboxes, where individuals can load data and explore and experiment. So much more going on here in data refinement than simple data integration, data warehousing style. And then the data consumption. Not only query for access, but data virtualization, APIs, and API management is a big part of data management today, and various kinds of data services. And our applications, as I've already talked about, expanding beyond BI and reporting to business analytics, data science, and again, the expansion of data consumers that I've already discussed. And then on this bottom tier, we have data management, and there's a lot of complexity here. Governance now includes data curation. We curate data sets for sharing, and we catalog those data sets. Data protection is a big thing. Privacy-sensitive data, security-sensitive data is very important. But governance also has to focus on data utility. How useful is the data in terms of quality, in terms of relevance, and ultimately on data value. How do we produce value from data? There's a lot of cost in managing this data. How do we get value in return from it? We also have to be concerned with metadata, the business glossary, data provenance and lineage, as I mentioned earlier, and the metadata that makes it capable to search for and evaluate and find the right data sets for self-service and analytics, the right data for data science projects. And we also want to collect metadata about usage of data and people's experiences with data so that we can begin to socialize this shared data in the right way. And supporting all of this, the combination of governance and metadata, there's that critical role of the data catalog. Also in data management, we have the whole master data environment, identity resolution, hierarchy management, producing golden records, maybe managing the data as an MDM hub, maybe manage it as master data services, maybe a combination of the two. We have administration as part of data management, security, servers, networks, databases, and administration of all the tools and technologies, which is a changing landscape all the time. And then our infrastructure, everything I mentioned about cloud, on-prem, hybrid, multi-cloud, plus the database management systems infrastructure, which is no longer just relational SQL databases. It's SQL in all the various forms of NoSQL, the analytics technologies, the pipeline technologies, and the technologies we use for automation and robotics. So a lot of stuff that goes on now in a modern analytics architecture. It doesn't look as simple as our old generation data warehousing architecture. So how do we get to a modern data architecture? I've defined it and practiced it and taught it as 4 steps. Identify business capabilities, explore business requirements, then identify data capabilities and requirements, and then adapt a reference architecture. At a high level, I'd say the first 2 steps are because we don't want to start with data, we want to start with business. Data before business, or it's hard to get value from the data. Then when we move to data capabilities and requirements, this is asking what features and functions and data capabilities our architecture needs to support. And the adapting a reference architecture says, don't ever start with a blank sheet. Start with something that is a framework, and then adjust that framework to become your architecture. And I will say, even though we call these things reference architectures, it's not really architecture until it has you in it, your company, your organization, your data, your processes, your expectations, your goals, your constraints and restrictions. It becomes architecture when you put you and your organization into it. Until then, even though we call it a reference architecture, it's really only an architectural framework. So this process is designed to turn that architectural framework into real architecture. Start by identifying business capabilities. Pardon me. This is the question of what does the business need to be able to do that can be effectively supported or enhanced with data analytics. So it's things like predict and plan and optimize and automate. Note that all of these are verbs. What does the business need to be able to do that we should be able to support with analytics? And I generally start when I'm doing consulting work with this list of 14. Inform about something, inquire about something, analyze the behavior of something, track something against goals, monitor the current state of something, send and or receive alerts about something, examine the alternatives for how to do something, simulate the behavior of something, explore patterns and trends, discover hidden insights, predict the future state, recommend decisions, or automate actions. So this is a starter list. This isn't an exhaustive list, but it is a lot of what we do when we support business with analytics. And we can think about these in terms of the products we build, the things we build to support these capabilities. Now, architecture doesn't build these things, but architecture needs to provide the guidelines for the builders of these things. So it's informed. We're talking about scheduled reports, ad hoc reports, self-service reporting. Generally, we're talking about reporting. If it's inquire about, we're talking about query capabilities. Behavioral analysis, we're looking at OLAP and self-service analytics. Tracking against goals, performance scorecards. Monitoring is dashboards. Sending and receiving alerts is about event monitoring and automated messaging. If we want to examine alternatives, we're into 2 kinds of analytic models, predictive and or simulation. Simulate the behavior is clearly simulation models. Exploring patterns and trends, discovering hidden insights. We do both of those with data mining. Predicting the future state, it makes sense that it's predictive analytics. recommend decisions is prescriptive analytics, prescriptive models. Automating decisions is prescriptive combined with AI/ML. Automating actions is AI/ML and software bots and mechanical or hardware bots. So we can begin to make sense of these capabilities and make them less abstract by thinking about them in terms of the things that will be built to support them. So if I know business capabilities, the next step is to think about business requirements, to consider what kinds of use of these capabilities. Instead of generic, give me specific examples, specific use cases. So asking questions, if the goal were to predict, then predict what? Who needs that prediction? Why do they need it? When do they need it? How often do we need to predict? Ask these questions, explore the business requirements. Now, you won't get an exhaustive list, but you'll explore business requirements in various domains. So this sort of looks like trying to explore business requirements around project management. And this comes from a consulting experience I had with a large city and their water bureau and managing their capital projects for developing water storage facilities, water purification facilities, for running water supply lines to various areas and new housing developments and so on and so forth, and the complexities of how those projects interacted with projects for street maintenance and traffic control and various other things. So many of the questions relative to this water bureau were about tracking project costs against the rate of completion of the project, tracking costs against goals, inquiring about budget level. So I won't read through all of these, but you can see that when I get from generic capabilities to specific use case examples, I need to go into user perspective, business perspective. What do people need to know to manage their work on a day-to-day basis? And then how does this translate to tracking and inquiry and prediction and exploration and exploring alternatives and so on? So what I want to do is get not an exhaustive list, that's not practical, but a representative list of business use cases, business requirements, based on my list of business capabilities. So inform about, maybe it's inform about excess inventory. Explore patterns and trends, maybe it's explore the patterns and trends of customer churn, or predict the future state of market growth. Now, many of these look like commercial enterprise, simulate profit and loss, but the same concepts apply whether it's commercial enterprise, nonprofit, or government agency. The need to be informed about something translates to specific examples in departments, in business functional units of what they need to be informed about. The need to explore translates to specific examples. So the goal then is to try to bring to the surface these very specific examples of what are some of the business requirements that represent these business capabilities. Then I want to shift from business focus to technical focus. What do we need to be able to do with data to enable these business capabilities? And it's important to remember that when we think about the business capabilities, we want to go back to the idea of what kinds of things do we build, analytic models, what do we build, OLAP capabilities to support these business requirements, and connect that then with how we are able to manage the data to support the business capabilities, to meet the business requirements, and to build the kinds of data and analytics products that we need to build. So then I want to consider data capabilities, things like data latency or volumes of data or quality or integration or the platforms that data is stored on, the platforms that data is processed on, data security, data access. So now I'm into technical things. And I want to itemize those in very specific terms. Support all data use cases. Support all data latencies from real-time to periodic batch. Support multi-cloud and hybrid data infrastructures. Sustain the value of my legacy data warehouse. Provide easy access for all data consumers. Work with all types of data. These are examples. Scalability, elasticity, security, protection, just a list of things that we need to be able to do that are the capabilities when working with data. And then for each of those data capabilities, I want to ask, what features must the architecture have? What are the required features of the architecture in order to support these data capabilities? So support all data use cases, I'm going to have an adaptable data consumption layer, adapt to every kind of use case. Support all data latencies. My architecture must include batch ETL, change data capture, and data stream processing. Support multi-cloud and hybrid infrastructure. I need to architect to include microservices and containers and cross-platform orchestration. Sustain legacy data warehouse value. Be able to ingest the warehouse into the data lake, and maybe be able to create the data warehouse, replicate the data warehouse as a data lake zone. So those are examples, and I won't read through the entire list, but you can see how important it is that I first think data capabilities, and then I translate those data capabilities into architectural features. What must the architecture do to support the data capabilities, which in turn support the business requirements and the business capabilities? So what else in data capabilities? There's a long list of these, and I can't even give you an exhaustive list. Do I want to be cloud first? Do I want to be streaming first? Do I require everything to be fully cataloged? Am I looking to maximize reuse, minimize redundancy? How important is trust and certification of data? Easy searching, maximum sharing, measured quality. The list goes on and on and on. And this is probably the most intense part of being a good data architect, is thinking through all of these capabilities, all of these features that an architecture must provide to be able to meet today's requirements and the requirements of the future, so we're not back rethinking architecture in 3 to 5 years. Then you can adapt a reference architecture. Don't start with a blank sheet. Use an existing architecture, reference architecture as a foundation. The one I showed you earlier is Eckerson Group Reference Architecture, because I work with Wayne Eckerson at Eckerson Group frequently, and I worked with Wayne to develop that Eckerson Group Reference Architecture. There are lots of others out there. Some are vendor specific, some are more generic. Forrester offers reference architectures. Gartner has some reference architectures, and the other analyst groups. And then there are some vendors who have reference architectures. Start with a reference architecture as a foundation. Choose one that makes sense to you, then adapt it to your business environment, your technical environment, your specific goals, your requirements. This is when it becomes architecture, not framework, is when you add your unique data sources, your specific business requirements, your specific data requirements. It works with your technical infrastructure and your technical capabilities, and becomes something that you can use to talk to all of your data stakeholders, the people who build those data and analytics products, the people who use those data and analytics products, the people who will support them, the technical people who have to provide capabilities to implement the architecture. This becomes the map of how we manage data. And to get there, you're going to adapt that reference architecture through a series of steps. Select the reference architecture. Don't hesitate to change the language. If you use different language than is in the reference architecture, use your familiar terminology. Then map the business capabilities to the reference architecture. Look at the reference architecture and ask how it supports all those business capabilities. Pardon me. Identify any gaps and adjust that reference architecture to fill those gaps. Map data capabilities to the reference architecture. You've expressed in data capabilities what features the architecture must have to enable those capabilities. Map them to the reference architecture, identify any gaps, and then fill all the gaps. Change that reference architecture until there are no gaps, no business capability gaps, no data capability gaps. That is your architecture. Now test it. Going back to that list of business requirements you built, run every one of those business requirements in a walkthrough or discussion forum. Run every one of those business requirements through that architecture asking how that business requirement will be satisfied by the architecture. And then finally, set forth some guiding principles for your architecture. If you've said support all data use cases, then maybe you want to express for those who do self-service analytics the kinds of use cases in self-service that are supported and how each one of them best interacts with the architecture. So guiding principles are just some guidelines for those who build data and analytics products about how to make best use of the architecture, how to get advantage from the architecture, how to use it well and be well aligned with it and get value from it and not be handcrafting or going off the map or rebuilding things, redesigning things that the architecture has already defined and designed. So from beginning to end, start with business requirements, then business capabilities, and data capabilities, data requirements, and then adapt that reference architecture so that it becomes your very own architecture. This is a very quick overview of a very complex process, but it's hopefully one that gives you some guide, some frame of reference in how to tackle this complex question of how do I get from my 1990s data warehousing business intelligence architecture to what I need as sustainable analytics architecture for the 2020s and well beyond. With that, I'll thank you. I hope it will prove to be valuable. I'll say don't hesitate to contact me. My name is Dave Wells. You can email me at david.wells@elearningcurve.com. You may also want to go to eckerson.com, pull down the blogs tab, and look for my name. And I've written lots of blog material out there about this approach to data analytics architecture. Once again, thank you.